Hi class, in today's video we're going to be talking about section 6.2, the sum and difference formulas. So up until this point we've really been looking at trigonometric functions, particularly at the end of chapter 5 and chapter 6. So these are the sum and difference formula. And so you might be asking, why do we need more formulas, right? We had a section on identities, we had multiple sections on graphs and their inverses. Well, our calculators are great in that, right, if we want to know, say, the cosine of pi over 12, we can put it in our calculator and it gives us this nice, neat decimal approximation. Remember, our calculators have to give us approximations because they can't represent irrational numbers like the square root of 3 and things like that. But sometimes having the exact answer or being able to come to the exact answer is more important. And so this is going to be the reason we introduce our sum and difference formulas for sine, cosine, and tangent. And so we'll have formulas for sine, cosine, and tangent. And then we're also going to take a little bit of look at what are called the cofunction identities. So for each sine, cosine, and tangent, we'll have sum and difference formulas. And then we'll have our cofunction identities. And without going into detail of why we have these identities, or formulas rather, I'm going to give them to you first. So for cosine, suppose we have the cosine of some angle u plus another angle v. So u and v in this case are both angles. If you'd rather, you could call them theta 1 and theta 2, theta and phi, it doesn't matter what you call them. But if we have the cosine of two angles added together, their result is the cosine of the first times the cosine of the second, and this plus becomes a minus sine of the first times sine of the second. And let me give you the one for subtract, and then I'll tell you why we might use these. So if we have cosine of u minus v, we have cosine of u times cosine of v, and this minus becomes a plus the sine of u times the sine of v. And a way to remember this is for your cosine addition or subtraction, you have cosine, cosine, the sign in the middle changes to plus or minus, and then you have sine and sine. So cosine, cosine, sine, sine, sine. So why might this be useful? Suppose we want to know the cosine of our friend pi over 12, right? And our calculator told us that pi over 12, its cosine is approximately, you can't see it, but it's 9.659. Well, I can look at that and I can be like, you know what? I recognize pi over 12. Let's rewrite pi over 12 as pi over 3 minus pi over 4. And just to do a little work on the side, pi over 3 minus pi over 4. So we have 4 pi's over 12 minus 3 pi's over 12 does give us pi over 12. So my math there checked out. And so the cosine of pi over 12 is exactly the same as cosine of pi over 3 minus pi over 4. And now why do I care that I can write it as pi over 3 and pi over 4? Well, I'll write up here in the corner our two important triangles. We have our pi over 4 triangle, which is our 1, 1, root 2. And then we have our pi over 6, pi over 3, square root. And that's our 1, 2, root 3. I said square root there. That's my 90-degree angle. My 1, 2, 3 right triangle, which means then the cosine of pi over 3 minus pi over 4 is cosine of the first times cosine of the second. You switch the sign in the middle, becomes a plus. Sine pi over 3 times sine pi over 4. And now we know cosine, SOHCAHTOA, cosine of pi over 3 is adjacent over hypotenuse. So adjacent over hypotenuse, that's 1/2, times cosine of pi over 4, cosine adjacent over hypotenuse, 1 over root 2, plus the sine of pi over 3, opposite over hypotenuse, root 3 over 2, times sine of pi over 4, opposite over hypotenuse, 1 over root 2. So here we have 1/2 times 1 over root 2, which is 1 over 2 root 2, and then plus root 3 over 2 root 2. Since they already have a common denominator, we can combine our numerators, 1 plus root 3 over 2 root 2. Now, if everything went as planned, if we take 1 plus square root of 3, divide that by 2 square roots of 2, 0.965925, blah, 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 all the way to that last digit, we have the same answer. You're saying, well, okay, so that worked. And just to give you a little bit more confidence, so this equals this. What happens if we type this string into our calculator? So if I do cosine of pi over 3 times cosine of pi over 4 plus sine of pi over 3 times sine of pi over 4, we get 0.9659, blah, 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 all the way down to that 3. So our calculator has confirmed that this does, in fact, work. And I'm not going to prove for us why this equation works. The book does go through why this works. It involves the fact that cosine of u, if it's some ray that looks like this, and v is some ray like this, well then, I'm just going to sketch it. I'm, like I said, not going to go through it. I can say that u, v, I can add v, and so here is u plus v, and it turns out that we can find our cosine adjacent over hypotenuse using this formula. Again, for this class, it's not important that you can figure that out, but if you're interested, it's in the book, it's there to read, or I'm sure you can find a video on YouTube. What's important here is that we're able to work with our formula. So another example, if we have cosine of 105 degrees. Well, again, what we can do is we can rewrite this. And so generally speaking, when we're working with our sum and difference formula, you want to find a sum or a difference of our special angles, right? And those are our 30, 60, and our 45. We also know our multiples of 90, 180, 270, and all of those. So cosine of 105 we can write as cosine of 60 plus 45. And so our first example had a difference. This one has a sum. So we have cosine, cosine, sine, sine, sine. Cosine of 60, cosine of 45, sine, that plus becomes a minus, sine 60, sine 45. And again, we know our cosines of these, so 60 degrees is pi over 3, adjacent over hypotenuse, it's a half, 45, 1 over root 2, minus sine of 60, so that's here, opposite over hypotenuse, root 3 over 2, sine of 45, opposite over hypotenuse. And so now we get 1 over 2 root 2 minus 3 over 2 root 2. So 1 minus root 3 over 2 root 2. Look at that. We had the same two values. That wasn't a mistake. But if we then go ahead, and now remember, if we want to do with degree, notice at the top it says radian, so we go to mode, switch radian to degree on our calculator. Now it says degree up top. I can do cosine of 105. It says it's about negative 0.259. And then if I do 1 minus the square root of 3, divided by 2 square roots of 2, negative 0.259. And I won't type this out again, but if you type sine 60 times cosine 45 minus that, you would get the same decimal approximation. But again, the value in this is that we can get the exact value of cosine of 105 degrees. This is our approximate from the calculator. But this is our exact value. And of course, we can't only go from, say, cosine of a number and decomposing it into a sum or difference. If we were, say, given an example that looks like, well, give the exact answer of cosine 57 cosine 33 minus sine 57 sine 33, we can work the opposite way, and so we can undo the sum formula. Because we have cosine, cosine, sine, sine, sine. So this is the cosine of 57, and this sign was flipped, so it becomes a plus. Our second number, 33. So we have the cosine of 57 plus 33, which is the cosine of 90 degrees. And that's if we have our xy, 0, 1, cosine, sine up here. Cosine of 90 is 0. We confirm that with our calculator. Cosine of 90 is, in fact, 0. And so we can work both directions with our cosine formula. And then for sine. So for sine, if we have sine of 2, that's the word sun. We'll just scribble that out and try again. Sine of u plus v. What happened was I was thinking about writing this u next, and my brain got ahead of myself. Sine of u plus v is sine u cosine v plus sine v cosine u. And so notice here, if this is u, we have sine of u and cosine of u. And if v is our second, we have cosine v and sine of v. So we have both sine and cosines in our final answer, and our addition sign doesn't change. And so for our difference, sine of u minus v, we have sine u cos v minus sine v cos u. So we're, again, for u, we have both a sine u and a cosine of u. And for v, we have a cosine v and a sine of v. And while up here, the order wouldn't matter because you can add in any way, it's important here that the subtract sign, this minus, because it stays the same, it needs to go with this term. So you could write this as negative sine v cos u plus sine u cos v. But I would say probably easier to remember it this way, because then if whether it's addition or subtraction, you always have sine u cos v, sine v cos u, and then you just keep the sign the same in the middle. So working with these values, or this formula, we have sine of 15 degrees. Find the exact value. So find the exact value of sine of 15. Well, that's the sine of 45 degrees minus 30 degrees. And if in our previous we had sine, cosine, sine, sine. If you want a way to remember this, it's sine, cosine, cosine, sine. So we have sine of the first, sine 45, cosine of the second, cosine of 30. The middle stays the same because there's no sine up there. Sine, cosine, cosine of 45, sine of 30. And I just realized, so this is a fun fact. So I remember the sine, cosine, cosine, sine. So in my brain, I actually flip these two. And why do I do that? Because then my u term always comes first. So actually how this is written, I have it written as sine, cosine, sine, cosine, which maybe isn't the most useful because I didn't say of what. So if I were to rewrite these again, and I won't for sake of simplicity, I would write it as sine u cos v, right? U and v. Sine u cos v minus cos u sine v. Cos u sine v. And I'll work through the next one again. So it's interesting how when we learn these, we have a certain order embedded in our memory. And so this is how it's written in our textbook. Sine u cos v plus sine v cos u. But because in my brain I remember it sine, cosine, cosine, sine, I have it in that order. All right, that's enough of diversion on that. If we want to figure this out, we have sine of 45, so opposite over hypotenuse, 1 over root 2. And then we have cosine of 30, adjacent root 3 over 2, minus cosine of 45, adjacent over hypotenuse, times sine of 30, opposite over hypotenuse. So here we have root 3 over 2, root 3 over 2, root 2, minus 1 over 2, root 2, root 3 minus 1 over 2, root 2. And that's what we get for our first example. We'll work through two more examples using our sine. Here we have sine of our friend pi over 12, which we already said we could rewrite as pi over 4 minus pi over 6. And actually this isn't how we rewrote it last time. Last time we wrote it as pi over 3 minus pi over 4. But this will give us the same answer, because our common denominator of 4 and 6 is 12. So we have 3 pi's over 12 minus 2 pi's over 12, which is still pi over 12. So see, there isn't even just one way that you could do this. You could do it either of these ways. I'm going to do it this way. I'll leave that one for you as an exercise. So here, sine of u plus v is sine, cosine, cosine, sine. Sine u cos v, cos u sine v. Again, there's a sine of u and a sine of v. There's a cos of v and a cos of u. So here we have sine pi over 4, cosine pi over 6 minus cosine pi over 4, sine pi over 6. So the other reason I prefer this order that I've written here as Oh, and it's crooked. I'll get better. Sorry about that, guys. So the reason we write it this way is because this first term, pi over 4, is first in both, and the second term, pi over 6, is second in both. So sine pi over 4 minus pi over 6. Well, we'll pull our triangles back. Sine of pi over 4, adjacent over hypotenuse, 1 over root 2. Cosine of pi over 6, root 3 over 2. Minus cosine of pi over 4, 1 over root 2. Sine of pi over 6 is 1 over 2. And if we get our like terms, we have root 3 minus 1 over 2 root 2. Not too bad. But something I didn't show you with cosine, which you can certainly do, is so the beauty of our angle addition and subtraction formulas isn't that it only gives us these two facts. What if I wanted to know the cosecant of pi over 4 minus pi over 3? I wrote that backwards, didn't I? Which one's bigger? Pi over 3? If I have 3 pieces, they're bigger than that. I wrote that backwards. Pi over 3 minus pi over 4. That's this one. Pi over 3 minus pi over 4. If I wanted cosecant, well, I know that cosecant is just 1 over sine of pi over 3 minus pi over 4. Well, that's 1 over sine pi over 3, cosine pi over 4, minus sine cosine pi over 3, sine pi over 4. Well, sine pi over 3. Sine is opposite over hypotenuse, root 3 over 2, root 3 over 2, times cosine 1 over root 2, minus cosine of pi over 3, 1 over 2, sine pi over 4, 1 over root 2. Well, that's 1 over root 3 minus 1 over 2 root 2. And then what we have here is we have 1 over this. So to get that to the numerator, we take the reciprocal. And instead, we have 2 root 2 over root 3 minus 1. So we actually know for angle addition subtraction, we know sine and cosecant and cosine and secant because of our reciprocal identities that we had in our last lecture. Now, sine and cosine. I said you would have to take my word on it because those were our angle addition and subtraction formulas, and it wasn't worth our time for me to prove it in this video. However, for tangent, this is one that's easy enough for me to show you the derivation. So tangent of u plus v is, remember, by definition of our quotient identities, sine of u plus v over cosine of u plus v, right? That's a definition we have. Tangent is sine over cosine. Well, and by our two angle addition formulas, sine of this is sine u, cosine v, sine cosine, cosine sine. So we have a sine u and a cos u, a cos v and a sine v. That looks good to me. And then our cosine is cosine, cosine, sine, sine, sine. So sine, cosine, cosine, sine, sine, cosine, cosine, sine, over cosine, cosine, sine, sine, sine. And you're like, well, that looks like a mess. We're going to divide everything by this term, cos u, cos v. And you're like, well, why? Why are we doing that? We'll see. Equals. So we have sine u cos v over cos u cos v plus cos u sine v over cos u cos v. We have cos u cos v over cos u cos v minus sine u sine v over cos u cos v. All right. So what happens? Well, we divided this by itself, so those all cancel and leave us with a 1. We have a cosine v in the numerator and the denominator, so they cancel. We have a cos u and a cos u in the numerator and denominator, so they cancel. And then nothing in that last one cancels. And now, sine over cosine of u is tangent of u. And sine over cosine of v is tangent of v. This is 1. Sine u over cos u is tangent of u. Sine v over cos v is tangent of v. So that means tangent of u plus v equals tan u plus tan v over 1 minus tan u tan v. And you might be saying, well, okay, I'm on board with that. What about tangent of u minus v? Well, in this example, we had a plus. And this, we know, the sign doesn't change. So if I have u minus v, then we're going to have a minus in the numerator. So tan u minus tan v. So this sign doesn't change, but this one does. So this minus becomes a plus, and we have 1 plus tan u tan v. So for tangent, tan u plus v is tan u plus tan v over 1 minus tan u tan v. Again, that sign in the denominator changes because of our cosine addition. But when we have subtraction, it doesn't change the numerator, it changes the denominator. So really, by knowing our sine and cosine angle addition and subtraction, that gives us our cosecant, our secant, our tangent, and then what does that also mean we know? Our cotangent with our reciprocal identities. So these two angle addition formulas give us angle addition for all 6 of our trig functions. So we'll work with a couple of these, and I'll go ahead and write them. So write this again. For tangent of u plus v is tan u plus tan v over 1. Sign changes because of the cosine in the denominator. Tan u tan v. And tangent of u minus v is tangent of u. Sign stays the same. Tangent of v over 1. Sign changes. Tan u tan v. So those are our 2 formulas. And I'll write our other ones here. Sine, cosine, cosine, sine, and cosine, cosine, sine, 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 just so they're all on one page. Tangent of 225 degrees. Well, that's tangent of 180 degrees plus 45 degrees. And so that means that this is angle addition. So we have tangent of 180 plus tangent of 45 over 1 minus, now the sign changes, tangent of 180, tangent of 45, put our degree marks in so we don't forget. And we'll go ahead and get our unit circle. 180 is over here, x is -1, y equals 0, that's cosine sine, and tangent is sine over cosine. So tangent of 180 is 0 over -1, so tangent of 180 is 0 plus 45 is our 1 root 2, tangent opposite over adjacent, 1 over 1. So 0 plus 1 over 1 minus 0 times 1. Well, 0 times 1 is 0, so we have 1 over 1, or 1. So the tangent of 225 is 1, and if our calculator is still in degree mode, which it is, tangent of 225 is, in fact, you can't see it, now you can, maybe for a little bit, is 1. We'll work through just a couple more examples with tangent, just to get practice working with the form of the tangent angle addition formula and subtraction. So tangent of pi over 4 minus pi over 6. We skipped a step. We already know what pi over 4 minus pi over 6 is. So we have our 1, 2, root 3. That's pi over 6, pi over 3, 90 degrees. 1 root 2, pi over 4, right, pi over 4. Keep our friends there. So tangent of this is tangent of pi over 4 minus, because it stays the same in the numerator, tangent of pi over 6 over 1, sign changes in the denominator because of cosine, tan pi over 4, tan pi over 6. So tangent of pi over 4 is 1 over 1, so we'll write this, tangent of pi over 4 is 1, tangent of pi over 6, opposite over adjacent, is 1 over root 3. So that means this is equal to tangent of pi over 4, 1 minus 1 over root 3, all over 1 plus 1 times 1 over root 3. So here we have 1 minus 1 over root 3 over 1 plus 1 over root 3. Now you could leave it like this. You could also do what's called rationalizing the denominator. And so if we multiply the top and the bottom by the conjugate, that's a fancy word for 1 minus 1 over root 3. 1 minus 1 over root 3. We're going to get the same thing on the top. 1 minus 1 over root 3 is times itself, so it's squared. Foil that, we get 1 minus 1 over root 3 plus 1 over 3, those cancel, and then the outside term, 1 over 3. It's not plus. Plus times a minus is a minus, so minus 1 over 3. 1 minus a third is 1 minus 1 over root 3 squared. 1 minus a third is 2/3. And so that's the same as 3/2 of 1 minus 1 over root 3 squared. Unless I specifically say to rationalize the denominator, you can stop. Let me get a different color. You can stop here. Stop here, unless it says to rationalize the denominator or to simplify completely. It's another way you might see it. But for my class, I'm good with this. If you want to keep going, I'm not going to stop you. And just as we could go both directions with sine and cosine, we can go both directions with tangent. So if I have tangent of 28 plus tangent of 17 over 1 minus tangent of 28 tangent of 17. Again, these are all degrees. This is, and how do we know if it's angle addition or subtraction? It's whatever this sign is and the opposite of this sign. So that's plus. So we have tangent of 28 plus 17. 28, 38, 45. Tangent of 45 degrees. We had that on our last page. Opposite over adjacent is 1 over 1 or 1. So this whole mess here equals 1. You might be wondering, well, what if instead we had this? What if we had tangent of 28 plus tangent of 17 over 1 plus tangent of 28 tangent of 17? Nothing. You're going to have to put it in your calculator because these signs need to be opposite. You either need to have a plus and a minus or a plus and a minus because of the form of our tangent, angle, addition, and subtraction formulas. So be careful with the angle or with the signs in that one. All right, so that brings together all of our sum and difference formulas. And I want to talk about the co-function identities. Suppose we have cosine of pi over 2 minus RV. Well, let's rewrite this. Well, this is cosine of v, negative cosine of v, plus pi over 2, right? All I did was swap their order. From our help students remember variables, we know that this is a horizontal shift and this negative sign is a reflect. So we have a horizontal shift and a reflect. Don't have a stretch or a shrink or a vertical shift. So this says we shift left pi over 2 and reflect about the y-axis. So for this, I have our friend cosine of v. We're a little crooked. Let's see if I can fix it. Y equals cosine v. And I'm going to put this transparency down. I'm going to use a color. I think brown will show up closely enough. And I'll trace our cosine function. I'm going to mark my origin just so I know where that point was. And remember I said that plus pi over 2 means we go left pi over 2. And then we reflect it around the y-axis, and so that means this point here. We're going to flip it, and we end up with this. Does that look familiar to anybody? Well, if I take that, this is our y equals sine of v. Notice those are exactly the same, or dang near close enough to it based on my scribbly handwriting. So the cosine of pi over 2 minus v is equal to the sine of v. So let me list all of our cofunction identities. So cofunction So if I have cosine of pi over 2 minus v, that's the same as sine of v. If I have the cosine, the sine of pi over 2 minus v, that's cosine of v. If I have the tangent of pi over 2 minus v, it's the same as the cotangent of v. I have the secant of pi over 2 minus v, that's the same as the cosecant of v. The cosecant, pi over 2 minus v, the secant of v. And our cotangent of pi over 2 minus v is tangent of v. So our cofunction identities tell us that if we have the sine or cosine of some value, we can offset it by pi over 2, and we get the other ones out. And so you'll have some homework problems working with these, but think of it this way. So if I had cosine of pi over 2 minus pi over 4, I don't have to use my angle addition formula. I could just say, well, that's sine of pi over 4. Which in this case, opposite over hypotenuse, that's my 1 root 2. 1 over root 2. And so this is particularly useful whenever we have angle additions involving pi's over 2. So suppose you had cosine of 135 degrees. Well, that's cosine of 90 plus 45. Well, cosine of 90 plus 45, well, that's not one of ours. But we do have minus. So let me think, why did I write 135 as this example? Because, ooh, that's tricky. Do I want to go there? No, I don't want to go there today. Yeah, we're not going to use our cofunction identities to talk about this, but how this, you know what, we'll do it. So this is, we need a pi over 2 minus an angle that we know. So we can do cosine of 180 minus 45, right? So that's 180 minus 40 is 140 minus 5 is 135. So let me, while that's true, we're not going to use it. Cosine of 180 is cosine, we could write that as 90 plus 90 minus 45, right? And I can look at that as two different angles. I can use angle addition here. See, this doesn't actually make our life any easier, but I'm going to go with it now. So we have cosine of 90, cosine of this, cosine of 90 minus 45, cosine, cosine, sine, sine, sine. See, this ended up being more work, but we're going to go with it. It's good practice. Cosine of 90 is what we have up here at our numerator. X is 0, y is 1. Cosine sine on our unit circle. Cosine of 90 is 0. 0 times anything is 0. Minus sine of 90 is 1. Sine of 90 minus 45. Well, sine of 90 minus 45, sine of 90 minus 45 is just cosine. So that's negative cosine of 45. And then negative cosine of 45, cosine is adjacent over hypotenuse, negative 1 over root 2. And if we draw 135 degrees, x is negative 1, 1 root 2, adjacent over hypotenuse, we get negative 1 over root 2. So these cofunction identities kind of help bring us a lot of things together. In this example, 135, it made it more work. Forgive me for that, but I still think it was good practice. And something I want to show you about the cofunction identities is that we can prove them. So our claim was cosine of pi over 2 minus v is sine of v. Well, if we use angle addition, so proof by angle addition, cosine of pi over 2 minus v is cosine, cosine, sine, 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 so we draw in our unit circle. Cosine of pi over 2 is 0 times the cosine of v, plus sine is 1 times sine v. 0 cos v is 0, 1 sine v is sine v. So cosine of pi over 2 minus v is equal to the sine of v. And that's how you would prove these cofunction identities are true. So, that being said, if you don't want to memorize these 6 cofunction identities, don't. I want you to know they have a name. I want you to know that they're a class and that they're helpful sometimes when we're working with some of our angles. However, if you again remember our cosine angle addition, our sine angle addition, so if we remember sine angle addition or subtraction and our cosine angle addition or subtraction, we get for free cosecant, secant, tangent, cotangent, and our cofunction formulas and identities. As long as we can remember our 2 special triangles, our 1, 1, root 2, which is our pi over 4 or 45 degrees, or our 1, 2, root 3 triangle, which is our pi over 6 or 60 degree right triangle, and our 4 important points on our unit circle, 1, 0, cosine sine, 0, 1, cosine sine, negative 1, 0, cosine sine, 0, negative 1, cosine sine. Thanks so much, everybody. I hope you have a great day, and I'll see you in the next